Hello. In this video, I'm going to give a quick demo of this notebook about probability fundamentals for deep learning. In the first code cell, this cell implements a complete classification pipeline from scratch using softmax and cross entropy laws. I simulate a neural network's raw output logic for four classes, converts them the probability using softmax, and then compute the cross entropy laws. So in the next one, I define entropy function and apply its four different probability distribution ranging from a perfectly certain prediction to a complete uniform one. We can see in the output. And then this in the next cell, I demonstrate the mathematical connection between cross entropy loss and negative long likelihood. I sweep over different predictions probability values and plot how both measures change together. In the next one, here I simulate neural network activation with a skewed distribution of a mean phi and standard deviation 3, then apply batch normalization to recenter and rescale them. And this cell uses a scipy.stats to plot the standard normal distribution alongside version with different means and standard deviation. In the next cell, here we are trying to show that the softmax function converts a raw network logics into a valid probability mass function where all values are positive and sum to exactly 1. Next is this cell visualizes both type of random variables side by side. The discrete distribution of rolling two dice shows a bar chart and a continuous distribution shows was a smooth probability density curve. Next, this is the main setup cell that imports NumPy and all the required libraries required, and the model, yeah. Next is here I visualize a neural network's output for an image classification task as a horizontal bar chart. The model assigns 85% probability to cat with the small probabilities to the other classes. Next, this cell simulates thousands of coin flips and tracks the running proportion of head after each flip. As the number of flips increases, the running proportion coverages towards the true probability of 0.5. In the next, I visualize the 6 equally likely outcomes of a single die roll as a colored squares, then show the resulting uniform probability distribution as a bar chart. In the next cell, this cell creates a full 66 grid showing all 36 possible outcomes when rolling two dice with the sum of 7 outcomes highlighted in red. It visually explains why 7 is most likely the sum, and there are 6 ways to make it outcome of 36. Next, here I visualize an event A and its complement side by side. Even though A is rolling is 6 and probability is 1 in 6, and it complements in rolling anything else with probability 5 in 6. Next is about addition rule in Venn diagram. This cell draws a Venn diagram to illustrate the addition rule for probability, and we can see like these are the OR, hot and OR king, and the final probability of it is shown in the output. Next is a tree diagram multiplication rule. Here I draw the probability tree diagram for flipping a coin and rolling a die to demonstrate the multiplication rule, and these are the outcomes of it. Next is verifying probability rule by simulation. This cell simulates 10 lakh coin flips and die rolls to empirically verify the multiplication and addition rules. Next is conditional probability. Here I visualize conditional probability using a deck of cards, showing the full deck on the left and only the face cards on the right after conditioning. So these are the outputs. Next, verifying the conditional probability formula. This cell verifies the conditional probability formula, and these are how the values come out to be after the condition probability is put. Next is Bayes theorem, medical testing population. Here I simulate a population of 10,000 people to visualize the Bayes rate fallacy in medical testing. Even with a 95% sensitive test, a positive result only means about 16% chance of actually having the disease when the disease is rare, and these are the following outputs. Next is Bayes theorem implementation. This cell implements the theorem as a function and applies it to the medical diagnosis, and these are all the outputs of the theorem after implementation. Next is visualizing belief update, prior likelihood, posterior. Here I plot a 3 bar chart side by side showing the prior belief before testing. the likelihood from the test results, and the update posterior after applying Bayes' theorem. And this is the visualization. The last cell, the final cell implementation sequential Bayesian updating, where each new test result is used as prior for the next update. It shows how receiving multiple positive tests progressively increases the posterior probability of disease and how a negative test decreases it, demonstrating that Bayesian interference is a continuous belief revision process. So, this is the final thing, and this is the summary of the whole notebook. That's it with this demo. Thank you.